Bismillahirrahmanirrahim. Welcome to week 5. So this lecture is about MOSFET, its internal structure, the all the junctions and how they are biased and how it operates. And in the end of this week lecture, we will go into the scaling. So what are the fundamental limits that the transistor is approaching? This slide is taken from a professor from Purdue University. So this is the three-dimensional structure of metal oxide semiconductor field effect transistor. So until now we have been drawing the transistor like this. So this was our drain, this was our gate, and this was our source. So we have been purposely neglecting the fourth terminal. So the fourth terminal is drawn somewhere like this, and it is called the body terminal. So we have a fourth terminal that is called the body terminal, and the voltage applied to the body terminal is called VP. So we have VS, we have VG, we have VD. Then we have the silicon dioxide layer, which is an insulator layer, and we have the metal gate. So this is the metal gate, and we have the source and drain regions. So this is an NFET or NMOS. And in an NMOS structure, the substrate is p-type. So and the you can say this region have a lot of electrons. So there are n-type, and the distance between these two is called channel length, or L. So this is the side view, and if we view it from the top, it looks like this one. So you have the gate, and on the sides you have the source and drain. So this dimension is quite important. This is the width, and another important dimension is channel length. So both these dimensions are very important for the electrical properties. For example, it is related to the amount of current that can flow in a FET, and we will see the equations and all those things. In this lecture, I have slightly deviated from the book because I want to convey the main ideas with minimal mathematics. So I found these slides with minimal math. That's why I preferred these. So the goal is to deliver all the concepts that are necessary, but keeping the math at a minimal level. So if we look to the transistor as a black box, we have four terminals. So we have a control terminal, we have this fourth terminal which was body terminal, and then we have the source and the drain. And there are many kind of transistors. For example, we have MOSFET, we have SOI MOSFET, we have FinFETs, and we have BJTs and JFETs and SPINFETs, and the list goes on and on. Okay, so but mainly we are interested in MOSFET in this course. So again, this is another picture showing the MOSFET. One is the actual photo from maybe from electron microscope or something, and it shows the transistor at nanoscale. You can see the source, the drain, the gate, and on the insulator regions and all these things. This is the body, and on here you can see the symbol of the MOSFET with gate, source, drain, and body. So you can consider the MOSFET as a two-port device, and the main electrical quantities of interest are these things. So we are interested in ID and VG, VS, and VD. And ID is basically a function of these things. So ID is a function of VG, VS, and VD. And if we look at it from the aspect of a two-port network, we see that we have at the input VGS. This is our input, and at the output we have VDS and this current ID. Okay, so this is our input side, this is our output side, and we have two separate names. So if we keep the VDS fixed and we plot ID versus VGS, we call this the transfer curve. So for example, a curve like this. So we have VGS, we have ID. This curve is called the transfer curve. We can have another one in which we have ID here and we have VDS here. Okay, and this curve is called the output curve. Okay, but the important thing is that in this one VDS is fixed, and in this one VGS is fixed. Okay, so one is called the transfer curve and the other is called the output curve or the output characteristics. Now, in order to understand the characteristic curve of a transistor, let me take you back to the Ohm's law. So on the right you see a resistor. This is well known to electrical engineers, and if you apply a voltage V across a resistor, you all know that V is equal to IR, or R is equal to V by I. So what that means is that if you plot the V on the x-axis and I on the y-axis, then you can plot a curve, and the slope of this curve is your resistor. So if you have a higher value of resistor, you will get a curve like this, which will mean that the current increases slowly when you increase the voltage. So it means the resistance is higher, and when the resistance is low, you have a curve like this, which means for a small change in voltage you have a large change in current. So this is the IV characteristic of a resistor, and you see the curve is what we call a linear curve. There is no non-linearity. Okay, so they are connected with, for example, they are not related with a square or a cube or something which are non-linear. Okay, so they are linearly related. Now the second thing that electrical engineers are accustomed to is ideal current source. So this is a ideal current source, and what an ideal current source provides is it gives you a constant current, you can say I0, irrespective of the voltage that is there. So the voltage can be anything along this axis, okay, but the current is always constant. So this is a ideal current source. Now interestingly, you can view the transistor as a combination of resistive as a resistor and a voltage controlled current source. So in this region you see it acts as ideal current source, and in this region, okay, from here to here it acts as a linear resistor. And you see we have VDS on the x-axis and ID on the y-axis. So we will call this curve our output characteristic. Remember that when we have VGS on the x-axis and ID on the y-axis, that was called transfer characteristic. Okay, so this is our output characteristic, but this is, you can say, ideally, but you know that the world is not ideal. So actually we don't have any ideal current source that gives us a constant current. We always have a non-ideal current source, which means that with the current source in parallel we have a resistor R0 which models the internal resistor of the current source. So R0 models the internal resistance of current source, and due to this kind of structure our curve looks like this and not like this. So that was for ideal, and this one is for actual. So the current is I0, which is provided, the constant current provided by the current source, plus another current which is equal to V voltage here across this resistor divided by R0, the internal resistance. So you have this kind of slope. So the same goes for a transistor, and you have the output characteristic curve something like this. So you have a smooth transition, okay, here. When you move from linear to this flat region, okay, later on we will call, the actual name for that flat region is saturation region, okay. but we will can use flat or saturation, anything you like. So we have a smooth kind of transition from linear to saturation region, and you see here the VGS is fixed at a certain value, which is VGS 1. So if I take maybe another VGS, so let's say this may be for VGS 2. Okay, so by changing VGS, the curve can move up and down. Okay, so here again you see that if you change the VGS, you get this family of curves. Okay, and so we have these three kind. Here one thing is important, that is this voltage, which is called VD set. So VD set is the voltage that below which is the linear region and above which is your saturation region. So this is the saturation region and this is our linear region. So VD set is the saturation voltage, and you see here is a subthreshold region which have a very this curve, which is almost the ID is almost like 0. So that is the subthreshold or cutoff region. So again the two curves, the output and the transfer characteristic, are shown. On the left you have the output characteristic, on the right you have the transfer characteristic. You can see that all the regions, the saturation, linear and cutoff, they are here and here. What is important in the transfer characteristic is this voltage VT, which is threshold voltage. So what is threshold voltage? If VGS is less than VT, okay, this will mean ID is equal to 0. So this region, so the transistor will be off, and when the VGS crosses the threshold voltage, the transistor turns on and we have a sort of exponential increase in current, but it depends on the value of VDS. So if you have a high VDS, the curve will go like this, and if you have a low VDS, the curve will go more slowly. Okay, so when the transistor is turned on, the amount of current is controlled by VDS. So the purpose of VGS is only to turn the transistor on or off, but the amount of current ID depends upon VDS. So these are two main applications of a MOSFET. It can be used as a switch in digital logic, which is this course, so all the gates and things, and it can be used in the analog world as a amplifier. I hope that you have taken a course in basic electronics and circuits where you have studied different kinds of amplifier. Just to wrap this part of lecture, so we have this kind of arrangement for an MOSFET. We have the source, which is normally held at low voltage, and the gate, which is held at a voltage that is above the threshold voltage VT, so the transistor turns on, and the voltage VD is also greater than 0 and the current ID flows. For a P MOSFET, all the things are opposite. So this is 0, this is less than threshold voltage. You can say the threshold voltage is negative in this case, and the ID flows here. So this is the whole story. Okay, let me stop here for this part, and we will continue with the next part.